This video is recorded to help my students to understand how to prove by mathematical induction. Mathematical induction is a method used to prove a statement P related to a subset of line-negative integer. This subset of line-negative integer has a starting point n0. n0 is line-negative integer. For example, if you want proof that for any n greater than or equal to 4 to the n power greater than 3 to the n power plus n squared. Now, this 2 is n0 is the starting point for this line-negative integer subset. That means for all the integers start from 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, keep going. For all those integers, 4 to the n power will greater than 3 to the n power plus n squared. Okay? Now, second example, prove that for any positive integer n, 24 divides 5 to the 2n power minus 1. In this example, this n, his starting point is positive 1. That means n0 is 1. So for all the integers greater than or equal to 1, then this is true. 24 divided by 2 to the 2n minus 1. The idea to prove this kind of statement, you need a two-step. First step we call base case. You prove the statement true. This statement is true at the starting point. So, for example, for the first example, you want to prove when n equal 2, this statement, this inequality is true. Then for second example, you need to prove when n equal 1, 24 divides 5 squared minus 1, which is 24. 24, of course, divides 24, right? That's true. So you need to prove the starting point, the statement is true. Then you need to prove the following statement. If for integer number k, the statement is true, then for his next number, the statement is also true. Please understand this step is you prove for k, if for k is true, then you can prove for k plus 1 is true. Now, if you combine these two cases, you say the second step basically say if this one is true and the next one will be true for sure, then combine with the first step, you have a starting point. For example, your starting point is 2. For 2 is true. Then based on the second step, since 2 is true, then for 3, this statement will be true. Now, since for 3 is true, then it will be true for 4, based on the second step. So basically, second step generate an automatic proof motion. Okay, so can keep going. That's proved for any n, this statement will be true. So let's you try the first example. Okay, so our base step. Then when n equal 1 or when n equal 2. Okay, then 4 to the n power. Oh, sorry. Let me insert this. 4 to the square, which is 4 to the n power, which is 16. 16 is greater than 3 to the square plus 2 to the square, because your n equal 2. 3 to the square plus 2 to the square is 9 plus 4, which is 13. So, base case, when n equal 2, the starting point, it is true, right? Because 16 is greater than 13. Okay? Now, then we prove the second is induction step. Induction. The induction case. That means we need to prove. Suppose that four to the k is greater than 3 to the k plus k squared. Now, based on that assumption, we need to prove that 4 to the k plus 1 will greater than 3 to the k plus 1 plus k plus 1 square. Now, that means based on this assumption, you need to prove this is true. So in order to prove this true, of course, I started from 4 to the k plus 1. Step by step, see what I can get. 4 to the k plus 1 power, that's definitely equal 4 times. You can see this is 4 times, I use multiplication here, times 4 to the k power, right? Now, by whatever your assumption, this will greater than 4 times 3 to the k power plus k to the square. Okay? Now, this step is based on your assumption. You assume 4 to the k power greater than 3 to the k power plus k squared, right? Now, then I expand it. So equivalent of 4 times 3 to the k power plus 4k squared. Okay. Now my goal is, say, if I can reach to this one, which is 3 to the k plus 1. Now notice 4 multiplied 3 to the k power can be written as 3 times 3 to the k power plus another 3 to the k power. Together is 4 times 3 to the k power, right? Then I notice 4k squared can be written as k squared plus 3k squared. Okay, k squared can be 4k squared can be written k squared plus 3k squared. Now, from here, let us begin to do some comparison. The first one, 3 times 3 to the k power is 3 to the k plus 1 power. That's equal. But k squared equal k squared, that's no problem. But 3k squared will greater than 2k. That's no problem, because 3k squared will greater than 2k, right? Because k squared will greater than k, and 3 will greater than 2. Then 3 to the k power will greater than 1. So, but this will give me, sorry, interrupted by a student phone call. I just answered the student phone call. Now, let's see. Let's continue. From here is, then we continue. This will be 3 to the k plus 1 power plus, notice k squared plus 2k plus 1 is k plus 1 square. Now, this is exactly what we want to prove. 4 to the k plus 1 power greater than 3 to the k plus 1 plus k plus 1 square. So equivalent, we finish the induction step, which is, suppose the statement is true for k, then the statement will be true for k plus 1 for sure. So after this step finish, we finish proof statement 1 by mathematical induction method. Okay? Now, let us say how to prove the 2. 2 says, for any positive integer, 24 divides 5 to the 2n power minus 1. Now, in this case, the base case is n equal 1. When n equal 1, okay, 5 to the square, 5 to the 2n, which is 5 to the square, minus 1 equal 24, which is divisible by 24. Okay, maybe I type wrong, which is divided by 24. Or always say 24 divides 24. That's no problem, right? Then induction step. Now, induction step, we need to prove. Suppose that 24 divides 5 to the 2k, 5 to the 2k minus 1. Then 24 divides 5 to the 2k plus 1 minus 1. Okay? Now, in order to prove this, we just say we start to consider this 5 to the 2k minus 1. What is the 2k plus 1 minus 1? What is that? So this is 5 to the 2k times 5 to the square. Because 2 times k plus 1 is 2k plus 2. 5 to the 2k plus 2 is 5 to the 2k multiplied 5 squared minus 1. Now 5 squared is 25. So this is 25 multiply 5 to the 2k minus 1. But 25 can be written as 24 plus 1. So this equivalent is 24 multiply 5 to the 2k plus 5 to the 2k minus 1. Now notice I rewrite 24 times 5 to the 2k as 24. I rewrite 25 times 5 to the 2k to 24 times 5 to the 2k plus 5 to the 2k. Okay. Now why I write in this? After writing this, I notice this sum can be divided in two parts. The first part is 24 times 5 to the 2k. This definitely is a multiple of 24, right? Then the second part, by your assumption, is also a multiple of 24 because 24 divides it. So the multiple of 24 plus multiple of 24 still multiple of 24, which means this is a multiple of 24. Then the equivalent say 24 divides. Then is 24 divides this 5 to the 2k plus 1 minus 1. Now that's we proved the induction step. Okay, so if you have any questions, please give me an email.